previous two lectures on harmonic oscillator, we looked at a free harmonic oscillator for which the equation of motion was k x equals 0. Then we looked at a damped harmonic oscillator where there was some damping proportional to the velocity, and the equation of motion was like this. We defined the quality factor, looked at this damped oscillator in the region of heavy damping, critical damping, and light damping. In today's lecture, we are going to look at another aspect of an oscillator, and we are going to ask what happens if I apply a force on the oscillator in addition to it being subjected to a force by the spring and its mass being m. The simplest case is that of a constant force on an oscillator, and you already know the answer. In this case, all that happens is that the equilibrium point gets shifted. You know the answer of this, I said, because you already know the example where if I take a spring, put a mass on it and put it vertically in the gravitational field. In that case, this is being pulled by a constant force mg, but still the equilibrium point shifts and still oscillates about the equilibrium point. To see it mathematically, let us write the equations of motion. Mx double dot in this case is going to be equal to minus kx plus whatever that constant force that I have applied, and therefore mx double dot plus kx is equal to f. Dividing by m, I can write this as x double dot plus omega 0 square x equals f over m, where omega 0 is square root of k over m. I bring f over m to the left hand side and write this equation as x double dot plus omega 0 square x minus f over m is equal to 0, which can be written as x double dot plus omega 0 square x minus f over m omega 0 square is equal to 0. Redefine y is equal to x minus f over m omega 0 square, or equivalently as x minus f over k, and your equation looks like y double dot plus omega naught square y is equal to 0, and I know the solution for this in general is y is equal to c cosine of omega 0 t plus d sine of omega 0 t, and therefore x is going to be equal to f over k plus c cosine of omega 0 t plus d sine of omega 0 t, where c and d are determined by the initial conditions. So, all that is happening is x has a constant shift and then it is oscillating about that point. More interesting case, however, is when we subject the oscillator to a force which depends on time. In general, a time dependent periodic force can always be written as a Fourier series like f n cosine of n omega t, where omega is the frequency of oscillation, and therefore, it is best that we analyze an oscillator subjected to one of these components, to a force f cosine of omega t, where omega is the frequency of the force. So, I am subjecting the oscillator to a force which varies like this with time. If I know the response of the system to f cosine omega t in general for any periodic force, I can find the response by superposing the solutions for each of these omega. In fact, I will assign you a problem later for two such forces being applied. For the time being, we focus on one frequency force being applied to the system, and therefore, the system I am looking at is a spring, mass at the end of it, and it is being subjected to a force f cosine of omega t. The equation of motion of this system is going to be mx double dot plus kx is equal to f cosine of omega t. If it is a damped oscillator, then the equation is going to be mx double dot plus b x dot plus kx is equal to f cosine of omega t. This is a free oscillator and this is a damped oscillator. And we want to look at the solutions of these two equations and see how they vary when omega is changed from one frequency to another in relation with the frequency of the oscillator itself, which is omega 0 is equal to square root of k over m. Let me first discuss the case of a free oscillator, because this will bring out the phenomena of resonance. So, for a free oscillator, the equation is mx double dot plus kx is equal to f cosine of omega t, which I can rewrite as by dividing by m, plus omega 0 square x is equal to f over m cosine of omega t. This is an equation which has a homogeneous part and a driving term. So, the general solution of this equation is going to be x t is equal to x homogeneous plus x particular. I need the homogeneous part to satisfy the initial conditions, because it is only the homogeneous solution that has freely fixable coefficients. So, this I can write as c cosine of omega 0 t plus d sine of omega 0 t plus x particular. The particular part of the solution depends on the driving term, and we want to find that. You see, this homogeneous part has two constants c and d, which will depend on the initial conditions. So, we find that for a free forced oscillator, for which the equation of motion is x double dot is equal to omega naught square x is equal to f over m cosine of omega t. The solution is x t is equal to c cosine omega 0 t plus d sine omega 0 t plus x particular. Now, it is very easy to see from these equations that x particular is going to be of the form some constant a cosine of omega t, because x if substituted here gives me cosine omega t, and second derivative with respect to time is also cosine omega t. When I substitute this here, I find that I have a cosine of omega t multiplied by minus omega square plus omega naught square a cosine of omega t is equal to f over m cosine of omega t. And therefore, since this equation is satisfied at all times, I get a is equal to f divided by m omega 0 square minus omega square. So, you see, for the particular solution there is nothing arbitrary, all the quantities are fixed, and therefore, the particular solution x particular is equal to f divided by m omega 0 square minus omega square cosine of omega t, and the complete solution of this equation x double dot plus omega 0 square x is equal to f over m cosine of omega t is xt is equal to c cosine of omega 0 t plus d sine of omega 0 t plus f over m omega 0 square minus omega square cosine of omega t. I have given you the full solution of a free oscillator subjected to an oscillating force. Coefficients C and D obviously depend on the initial conditions. Let us now take an oscillator on which I start applying this force such that initially it is at 0 position at its equilibrium point, and it also starts with 0 velocity. X dot is also 0, and I want to determine coefficients C and D accordingly. When I substitute x 0 equals 0, I get 0 is equal to C plus f over m omega 0 square minus omega square, or C is equal to minus f over m omega 0 square minus omega square. Similarly, when I take its derivative x dot, it will give me minus omega c sine omega 0 t plus omega d cosine of omega 0 t plus f over m omega 0 square minus omega square times omega sine omega t with a minus sign here. And since I know x dot at 0 is 0, it gives me d is equal to 0. And therefore, if I take an oscillator subject to it to a force f t equals f cosine of omega t and its natural frequency is omega 0, then the general solution starting with 0 velocity from the equilibrium point is going to be C, which was minus f over m omega 0 square minus omega square cosine of omega 0 t plus f over m omega 0 square minus omega square times cosine of omega t. This is the general solution. Let me write it clearly on the next page. So, general solution for a freely oscillating particle with natural frequency omega 0 subjected to a time varying force which is f cosine of omega t is x t is equal to, let me take this out, m omega 0 square minus omega square cosine of omega t minus cosine of omega 0 t. This is the general solution. This is under the condition that x 0 at time 0 and velocity at time equal to 0 are 0. How does this solution look? It has two frequency components, omega t and omega naught t. So, it is obviously not harmonic, but it is a superposition of two different frequencies. If I were to make this on a phasor diagram, which gives me an analysis of this. So, I am looking at the solution x t is equal to f over m omega naught square minus omega square cosine of omega t minus cosine of omega 0 t. Suppose I would look at it at t equal to 0. At t equal to 0, the term f over m omega naught over omega square cosine omega t looks like this, and at the same time the other term is in the opposite direction. This term is this one. After time t, this term goes to, this phasor moves by an angle omega t. Let us assume right now that omega 0 is larger than omega. In that case, so applied frequency is smaller than the natural frequency. This phasor will move slightly more, maybe it comes here by omega 0 t. So, to get the net displacement I add it to this one, and let me show by red, the net displacement is going to be like this. After some more time, say t2, this fellow may come here. Let us say this is omega t2. This will move much more. So, this will come, say, let us say here. So, at that time, this the net displacement would be somewhere here, it will be somewhere here. You see, not only has the amplitude changed, it has also moved. So, it oscillates obviously between these two extremes, but the amplitude keeps on changing. If I were to see this displacement and plot it on displacement versus time plot, it would look something like this. It starts, the amplitude goes up, comes down, starts again, goes up, comes down, goes up, comes down, and so on. So, the amplitude sort of changes with time. I have given you a general sort of behavior when these two frequencies are superimposed. What I would urge you to do is do an exercise, choose an omega 0, let us say some number 2, choose an omega equal to 1, choose another omega 1.5, choose another omega 1.7, and so on, and try to plot these. I would give you a general feature that as you approach closer and closer to 2, you would see that this amplitude thing goes really far out and then goes down. But I would really like that you solve, you know the answer, solve these problems for 3 different omegas and plot it and see how the amplitude varies. What would be a very interesting question to ask now is, what happens when omega equals omega 0? Recall that the solution is x t equals f over m omega 0 square minus omega square cosine of omega t minus cosine of omega 0 t. I cannot substitute omega equals omega 0 directly here, because when I divided I assumed omega and omega were not equal. So, I take the limit omega going to omega 0. So, let me take omega to be slightly smaller than omega naught and substitute it here. So, x t in this case would be f divided by m times 2 omega 0, because this delta is very small, times omega 0 minus omega 0 plus delta times cosine of omega 0 minus delta t minus cosine of omega 0 t. So, this comes out to be f over 2 m omega 0 delta times cosine of omega 0 t, cosine of delta t, and delta being very small, I will take that as 1, plus sine of omega 0 t times sine of delta t, which I will take as delta t because delta is very small, minus cosine of omega 0 t. In fact, delta finally I am going to take the limit of going to 0. This cancels. So, this answer comes out to be, this delta will then cancels with this delta, f over 2 m omega 0 times t sine of omega 0 t. What do you observe? You observe that x increases with time linearly. If I were to plot this, it would look something like this. X t I am plotting as f t over 2 m omega 0 sine of omega 0 t. Remember, when I take delta equal to 0, this is an exact solution. So, it will look something like this. You see this part goes up linearly. This is the phenomena of resonance. So, when omega, the applied frequency, is exactly equal to the natural frequency, the oscillations grow linearly with time, and finally the amplitude becomes very, very large, and in fact so large that the oscillator may break. I am doing this phenomena here for free oscillator because later we will see when we put damping in, resonance does not mean that the amplitude keeps becoming larger and larger, rather it shows the maximum amplitude.